Okay, so let's start by defining this notion that'll be helpful. We'll talk about a game sequence as any sequence of threes or sevens, a finite sequence. So 333, that's a game sequence. You can have a mix of threes and sevens. This just represents the sequence of scores that a team could make in this problem. And then what we're asked to do in this problem is to find a least natural number such that for anything bigger, there is some game sequence whose sum is this number n. And the first thing that we have to do is we have to decide what we think n naught is, because that's some specific number, right? It is uniquely determined by this problem, so we actually need to find what we think it is, and only then can we prove that it has the properties that we claim it has. If you go through the numbers in order and just look for ones that cannot possibly be produced by any game sequence, you find that as you go along, 11 is the biggest number that is not the sum of any game sequence. And you can show that just for the sake of time, because these videos have to be less than 5 minutes. I'm not going to talk through the logic of how you show that, but you can kind of see it here in what I've written up. But 12 is the sum of some game sequence. I've written it here. And in fact, it turns out as you think about going beyond 12, every number is the sum of some game sequence. So 12 is the number that we are going to hypothesize is this value of n naught, and then we're going to prove it by strong induction. Now, because sort of the least jump that these sort of points make in a certain rough sense is 3, then I might want to do my proof by strong induction with 3 base cases. And that'll mean that when I get to the inductive part of the proof, I can always refer back 3 cases and use that step size 3 to connect the inductive hypothesis to what I'm trying to prove. So anyway, we'll see more about exactly how that works. But let's just talk briefly about the base cases. So the base cases are going to be 12, 13, and 14. And I have written here explicitly demonstrations that each of those are the sum of some game sequence. So there's that. We will now move on to the inductive hypothesis, or the inductive step. With this inductive hypothesis that if n, we now assume is at least 14, because I proved the base cases for 12, 13, 14. So now I want to make my inductive step starting at 14 and going to anything next. And so for inductive hypothesis, we will assume that the claim is true for every number between 12 and n. We then want to prove that it's also true for n plus 1. Now, because I can refer back 3 steps, then I'll do kind of what the plan was all along. Split off a 3. This is how you do that, leaving an n minus 2. N minus 2, it is easy to argue, is between 12 and n, and therefore the inductive hypothesis applies. And from there, we know that n minus 2 must be 3a plus 7b for some natural numbers a and b. We can then do some algebra to take that split apart, replace n minus 2, leaving this extra term 3, put the things that have a multiple of 3 together, and now we have that n plus 1 is 3 times a natural number plus 7 times a natural number, and that means that there is some game sequence which sums to n plus 1. So that effectively concludes the inductive case. That means we have concluded the inductive proof, and therefore we can conclude exactly what the inductive proof was trying to show.